but in principle, it is very important also in theoretical mathematics. In many interesting theories, we can use inverse matrices to develop these theories to solve problems. However, for you, what matters is being able to find the inverse matrix of a given matrix. And yes, we will have one serious application for solving systems of equations. So the definition of inverse matrix. First of all, we will consider only square matrices. But secondly, there's another thing. First of all, I would like to use a comparison. When we have numbers, the numbers usually come in pairs. There is such an idea as reciprocal numbers. When we talk about numbers, for example, the number, okay, no, let's go back. And I need this. No, not black, not red. There's white. Okay. So if I have, for example, two numbers, 3 and 1/3, these numbers are called reciprocal numbers because the product is 1. Similarly, for example, 2/5 has reciprocal number 5/2 because the product is 1. So with numbers, it's easy. We simply write it as a common fraction and turn it upside down. And those are reciprocal numbers. Two numbers are called reciprocal if the product is 1. And then, of course, 0 does not have a reciprocal number because 0 times what would be equal to 1? There's no such number. And 1 is reciprocal to itself, of course. Now, with matrices, the general idea is that we do the same. If the product of two matrices is 1, then these two matrices are called not reciprocal. We use the word inverse. Only the problem is, what does it mean, 1? And here it's the time to remember the unit matrix or the identity matrix. Remember that the unit matrix was the matrix that has 1 in all elements on the main diagonal and zeros everywhere else. So this is the identity matrix 3 by 3, third order identity matrix. Second order identity matrix or unit matrix would be 1, 0, 0, 1. Fourth order identity matrix would be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. That would be the fourth order. Fourth, that's I, that's not T. Identity matrix. So if I multiply two matrices, square matrices, and the product is the identity matrix or the unit matrix, then we call them inverse, mutually inverse. In principle, this identity matrix, we already considered it in the first lecture, it serves the same purpose as the number 1 in number algebra. In matrix algebra, the unit or the identity matrix is the same as the number 1 in ordinary algebra. And so the inverse matrix is denoted by, we do write A seemingly to power minus 1. We never read it as a power. It's not a power. It's not a power. We do not divide because we do not we do not write this. Never write 1 divided by a matrix because that's completely wrong. You cannot divide by a matrix at all. So the inverse, simply notation, A inverse. And so by definition, A times its inverse, A times its inverse is the identity matrix. And I made a mistake. I think I didn't write it backwards. Also, A inverse times A is also the identity matrix. Here, the order was not changed. So it doesn't matter which which order you use. So this is one of the very, very rare situations when matrix A times matrix B is the same as matrix B times matrix A. It happens very, very rarely. But with the inverse matrices, it's always the two inverse matrices. You can multiply first by second or second by first. It's always the same thing. It's always the identity matrix. That's the definition. That's the definition. Now the question is, how do we find it? That's a serious question, because if you don't know how to find the inverse matrix, then what's the use of defining it? So the size is of course the same. It will have the same size, the same shape, square matrices, same order, of course, naturally. But how to find it? Now let us see. We have the cofactor method. In principle, theoretically, it is of course possible. It is of course possible to denote the matrix, right? The matrix elements like A, B, C, D, E, F, G, H, I, then multiplied by the given matrix, whatever it is. So we would say these are known numbers, if we know these numbers, and then we have 1, 1, 1, all those zeros for the identity matrix, right? We could solve it like an equation. So we don't know what the inverse matrix is. We do know what the given matrix A is, so we would have definite numbers there. So we could, of course, use algebra, use matrix multiplication to write equations. We would have number times A plus number times B plus number times C equals 1. Some other number equal times ABC equals 0, and so on. We could write actually a system of 9 equations in this case, which is, you will agree, totally too much. Nobody wants to do this. So in principle, of course, in principle, it is possible to demonstrate that this method would work, and that by this method we can also find the general formula for an inverse matrix of, for example, 2 by 2, 3 by 3, but it would be very messy. It's a lot of work. So we will have a very general matrix. So we suppose that A is a square matrix, and then the plan of action or the algorithm for finding the inverse matrix is, first of all, we find the determinant. We find the determinant of the matrix. That's universal. You can't do without it. Now, next, find all the cofactors. Remember, cofactors were the minors with sometimes an extra minus, and form the cofactor matrix C of the given matrix, which means every element ij from the given matrix is replaced by its cofactor. That will be the cofactor matrix C, only by cofactors. So we replace existing elements by their cofactors. Remember that cofactors will be numbers in the end. They will be numbers, of course. So we replace numbers from the matrix by some other specific, very specific and concrete numbers. Then we will transpose the cofactor matrix. Transposition, remember, it was flipping it across the main diagonal. The matrix transpose of C, okay, sorry, that was an accident. The matrix C transpose is called the adjoint matrix of A, the adjoint matrix of A. And you can write C transpose, or you can write adjoint of A. That's the same thing, exactly the same thing. Adjoint matrix, which already tells us, the name itself already tells us that this matrix is somehow joined to the matrix A. It's some matrix related to A. It's connected to A. Of course it is, because we found the cofactors, and the matrix actually consists of cofactors. And then finally, the inverse matrix is found as we take this adjoint matrix that we constructed from cofactors, and transpose then, and multiply by this number, 1 divided by determinant of A. So that's why we needed to find the determinant of the matrix, because cofactors is not enough. We have to multiply by the reciprocal of the determinant. There's one thing, of course. If determinant of matrix is 0, then the division is impossible. We cannot divide by 0. So determinant of the matrix cannot be equal to 0. If it is 0, then evidently the division is impossible and the inverse does not exist. So we call this matrix, in that case, we call it singular. If the determinant is 0, then the inverse matrix does not exist. And therefore matrix A is called singular, as in lonely, only, without a companion, singular as in single. There's it's just itself, and it doesn't have an inverse matrix. In number algebra, there's only one such number 0 doesn't have a reciprocal. But in matrix algebra, many matrices are singular. They don't have inverses. Now let's try it. We will consider, first of all, a special case, the inverse of a 2 by 2 matrix. Let's see. Suppose we have a 2 by 2 matrix. In principle, we can do it according to this plan I just described, but in practice, it actually is. A little bit nicer. So what we do? Okay. What we do is, let's see, the determinant, of course, the determinant of the matrix A is AD minus BC. We know that. Let's suppose it's not 0. Suppose it's not 0. Suppose it's not 0. If it is 0, we know that that's nothing, we can't follow. But let's suppose it's not 0. Then let's find the cofactors. Cofactor 1, 1. Now the sign diagram is plus, minus, minus, plus, just board principle. Cofactor 1, 1, okay, eliminate this, and you get, it's just the element D, because everything else is crossed out. Cofactor 1, 2, cofactor 1, 2, 1, 2, first row, second column is in the minus position. And its cofactor, of course, is minus C. Because if we cross out the row and the column of B, we only have C remaining. Similarly, cofactor of 2, 1, that is cofactor for C, is minus position. C is in the minus position. And that cofactor is B, because we cross out the row and the column, we get B. And the cofactor 2, 2, that is the cofactor of element D. D is in the plus position. Sign doesn't change. Cross out that row, that column, and we have A. So the cofactor matrix is, instead of A, instead of 1, 1, we have D. Instead of B, instead of 1, 2, we have minus C. Instead of C, 2, 1, we have minus B. And instead of 2, 2, instead of D, we have A. That's the cofactor matrix. Now the adjoint matrix of the given one, or the transpose of cofactor matrix, is transposition. Remember, we flip it. No, that's not what I wanted. This was what I wanted, I think. No. Okay. It's not very helpful. Oh, there we have the pointer. Okay, there we go. So just remember that to find the transpose, we have to flip it across the main diagonal. We flip it across the main diagonal. So D and A remain, and minus C and minus B exchange places. Okay, let's go back to pen. And so we have D is where it was, A is where it was. Now these two flip places, minus B, minus C. This is the adjoint matrix. And so the inverse, for the inverse matrix, we only need to do 1 divided by the determinant times this, D minus B minus CA. So in fact, to find the inverse of the 2 by 2 matrix, notice what we can do. We can simply exchange, we can exchange the the two elements. Let me erase and clean up the given matrix. It's a bit dirty, messy with my chalk. So see what happens. A and D on the main diagonal, they are simply exchanging places, they swap places. And B and C, minus B, minus C, they don't swap places in the end because they did it once for the cofactors and they did it back for the transposition. But they only change the signs. So for D and A, we change places. For B and C, we only change signs. And so finding the inverse of a 2 by 2 matrix is very simple, in fact. However, as far as I know, many people prefer to do the cofactors. Just remember that a cofactor is the remaining element with an extra plus or minus sign as necessary. So there you have the formula written in a nicer way, in a printed way, so it's more easily read. So that would be a special case. So many people actually memorize this. And when we have a 2 by 2 matrix, just do it. So an example, this one. Let me remind you. So the inverse was 1 divided by the determinant A, and then we had D and A exchange places, but B and C only get the opposite signs. So for this, the determinant of A is 5 times 1 minus 3 times minus 2. That is 5 plus 6 is 11. That's fine. And now the inverse, I can in fact write it immediately. So it is 1 over 11 times. Now D and A get exchanged. So I have 1 and 5. And 3 and minus 2 simply get the opposite sign. So 3 becomes minus 3 and minus 2 becomes 2. And that's the inverse matrix. Now the remaining thing is we can, or sometimes we choose not to do it, bring the factor 1/11 into the matrix. So we could have 1/11 minus 3/11, 2/11, and 5/11. So this is the final answer. However, in many cases, we leave this clumsy factor outside. We just leave it outside. Now, I know that you are used to using your calculators and finding approximate values. In principle, in most cases, I'm absolutely not interested in approximate values. I'm only interested in the exact values because those reflect your, let's say, mathematical logical thinking. And so we may leave a factor outside if it's like a fraction. If we see that the inner matrix the inside of the matrix would look not so very nice, then we can actually live without it. We can leave it outside, and then if necessary, if we need to do something with this matrix further, then we might find a good moment to multiply by that number. But as it is, we can leave it like this because it still makes perfect sense. Okay, I forgot to put an animation to this, unfortunately. All right, a method for cofactor method, an example for cofactor method. That's the last thing we do today. Then we will finish this. Okay, somebody has disappeared. And so the example, this matrix actually is familiar. The determinant of this matrix is something we found on Friday. It's minus 40. We did it on Friday. We had it. We had this matrix Friday or Wednesday, but we had it. It's the same matrix. Now, to do it perfectly by the cofactor method, so I'm just trying to save time now. By cofactor method, it is advisable to place the cofactors in their correct places. Then you don't have to write the matrix C separately. So I would write cofactor 1, 1, then I would write cofactor 1, 2, then I would write cofactor 1, 3. And let's see. 1, 2, 3. I'm also remembering the plus minus plus principle, the diagram. In principle, you don't have to write it, but actually, if you write it down, it reminds you of what you need to do. So cofactor 1, 1 is the cofactor that you get when you eliminate row 1, column 1. So basically, this is the element 1, 1. You eliminate that row, that column. So this cofactor is 0, 5, minus 1, 2. And actually, it is 0 minus negative 5. It is 5. It's not 6. It's 5. Okay. 5, not 6. 1, 2. 1, 2 is in the minus position. So we have to write minus minor. And the minor of that element is 4 minus 2, 5, 2. We see it's 8 minus negative 10. That's 8 plus 10. That's 18. And this extra minus in front gives us minus 18. With this extra minus in front, minus was from the diagram, this. So that's why we changed the sign. C13 is in the plus position, so it would be this minor. So it is 4, 0, minus 2, minus 1. 4 times minus 1 is minus 1, minus 0, it's still minus 4. 4 times minus 1, minus 4. Now C21 is in the minus position. Cross out row column, you get 3 minus 1, 2. Again, you find the value, you evaluate. Then you write C22. It's in the plus position, so we write it as it is. Cross out, you get 2 minus 1. 2 minus 1, minus 2, 2. Then C23 would again have this extra minus. And similarly, the last row. In that case, you would see that you get this cofactor matrix already done. So in principle, you would have the numbers already there. 5 minus 18 minus 4. Then you would have, I think this was minus 5. Then we would have, this was 2, and then we would have minus 4, and so on. Or something. But what we do now, we don't have to always rewrite the whole cofactor matrix. You can actually leave it as it is. Or you can make a nice table. If you look at the lecture transcript, I deliberately put all those cofactors in a table in their proper places. And then what you do is you simply flip it. See, now the cofactor matrix would be 5 minus 18 minus 4 minus 5 2 minus 4 15 minus 14 minus 12. I'm cheating. I'm looking at my answers, of course. But that would be the cofactor matrix. From there, you may write it as it is separately, or you may just see these elements in their proper places in your table. And then when you transpose, this is the transposed matrix. This is the transposed matrix. Then the next step would be take the C transpose, that's the adjoint matrix, or C transpose, this one. See, the first row became first column, the second row has become the second column, and the third row has become the third column. So this is transposition. This is transposition. Each row becomes the corresponding column. I will perhaps use some color, okay, to remind those people who missed the first lecture on Monday, for example. When we transpose this transposition process, first row becomes first column, second row becomes second column, if you like this, see? And the third row becomes the third column. And then finally, if you feel like it, because dividing by 40 is not something very nice, on the other hand, we get finite decimals. We have finite decimals, not too long, so that's fine. Not more than 3 decimal figures, that's perfectly acceptable. However, it's easier to perceive, it's easier to read the matrix in this form. It's much easier to read it in this form than in this form. So in principle, I am not requiring that you do this. You don't have to always multiply the coefficient into the matrix. If it's an integer, then yes. But if we have some unpleasant fraction, then perhaps it's not worth the effort too much. All right. So we have spent a lot of time on both things, on doing revision of determinants and also on finding the inverse matrix. On Wednesday, we will go on with exercises for inverse matrices, perhaps some more exercises for determinants. And yes, that's on Friday. On Friday, we are starting something new again. We are entering the final curve, or a final straight segment of our first unit. That is solving systems of equations. All right. I hope everybody wrote their name in the Zoom chat, so then I can actually take attendance. So if you have questions about elementary mathematics, please email me. I will answer as best as I can. And please remember to take the elementary mathematics test. It's diagnostic. It does not influence your semester grade. Please don't worry about that. The elementary mathematics test as such, even if you have a 5, that means you have passed it, it will not influence your semester grade. This test is simply to see which people really need this revision course, elementary mathematics. And of course, I've seen there are some people who want to take it for the sake of improving their mathematics. They will not be required to pass all 4 tests. However, writing those 4 tests would be advisable just to test yourselves. The assignment that goes for Mark, the home assignment, will be posted this week, maybe Wednesday, maybe Friday. I would prefer to do it Friday because until Wednesday, I'm still accepting people in this course. So those people who don't show up until Wednesday, they won't be accepted in this course anymore because they will have missed too much. This is about as much as they can afford to miss, to find the matrix operations and up to finding inverse matrix. The rest is too important, they cannot miss it. So, in principle, I could do it. I could do it even today, but I still want to see who shows up on Wednesday of those people who never showed up until today, for example. There might be some people who just come on Wednesday, so I need to count properly. But basically, Wednesday afternoon then probably. All right, so if you pass the elementary mathematics test and still think that you need that revision about those topics that are in the elementary mathematics, then please email me and I will add you to that course. And if you get less than 4, then you must take elementary mathematics. And if you ignore the elementary mathematics test, then you automatically are added to elementary mathematics and must take it anyway. So better write the test and see what happens. All right. I will see you on Wednesday, the early class. So those who are here in Latvia have to wake up early. I guess most of you are at home anyway, but who knows? So 8:15, Wednesday morning. And bye for now.
Okay, thank you for the lecture.
You're welcome. Yes.
Ma'am, can you add the answers for the assignments you have given on that Otis?
Which the lecture files? Oh yes. You said the one of those lectures had no answers. I will check it. I will check it. Yes, the second and third also.
Yeah, ma'am.
Okay, I will check it. All right. Yes. Thank you for reminding me.
Thank you, Professor.
You're welcome.